Does that mean you're ready this time?
It means I'm ready.
Hello again. We're still here. A second thing to do while we've got this apparatus out. This one is slightly dangerous, so it's probably better if we actually do this one with no one around, except our good selves, who don't matter at all, apparently. This time we're going to have a go at whirling things in a vertical circle. Our aim this time will not be so precise in measurement, rather to actually use the computer to its full power to demonstrate an idea we've already met. That when moved in a vertical circle, there will be a variation in tension between a maximum and a minimum value. In fact, if I might just remind you of this idea, a mass moving in a circular path will vary in the tension required to keep it in that circular path. So if we take three positions, top, bottom, and one somewhere near the side, let's just think about what's going to happen to the tension that's connecting that to the centre of rotation. Now, in all cases, it will require the same centripetal force if it's going at a steady speed in a circle. And that, obviously, will be directed towards the centre. And its size, as we've already explored, we can now rely on as m omega squared r. However, because it's going vertically, the support has to do more and less work at different stages of the cycle to keep it going in a circular path. To provide a force that is that size for the circular motion requires the actual support line at the bottom to additionally support the mass, the weight of it against gravity. So m omega squared r plus mg. And that's what we'd expect to see as our maximum value of tension. At the top, gravity is already providing some force in that direction. And so I hope you remember, or it's clear to see, that we will not provide that bit of force without tension in our connector. So that should be our measurement at the top. And just for completeness, at the side, obviously there is no component due to weight in the direction of the force towards the centre. So this has no effect, and we should expect the centripetal force to be m omega squared r plus nothing extra. So as it turns, then, as this is measuring, using our wireless system, directly the force, the tension in that line, we should expect to see this variation. And we can predict the size of the variation. The variation should clearly go from a mean position, m omega squared r, and it should become smaller by the value mg and larger by the value mg. In other words, a total spreader result of twice mg, 2 lots of the weight of the thing. We're using the same mass as before. You may remember from before, it's not just the mass rotating, we know now it's the mass and the hanger. And so, mg should actually have a real value. Mass, the best we can get that is 0.102 kilograms. The value of g we'd use would be 9.81 for that. And so working those two out together gives me a value of 1.0062. So to significant figures, we're actually aiming for that to be 1.00. That should be our variation that we see. As ever, I'm still looking for a beautiful assistant. In the meantime, Colin has kindly offered to fill in on making sure this bit is running correctly, though while we're taking the readings, it'll be no more than pressing it and standing well back, though I didn't build this equipment, so chances are quite good it will make it through the afternoon. Okay, let's just see if we can get it set up. We'll aim for some slightly higher forces than last time to show this more clearly. probably starting at around 10 newtons of centripetal force, then actually going up periodically. We'll only take 30 or so seconds worth of data. I won't talk while that's going on because it's very noisy when this is actually happening. Okay, ready?
Yeah, if you want to start it up and get it at a steady force of around 10 newtons, and then we can start collecting the data. Okay, yeah, that's fine, okay. So we'll start collecting data at that point there. That should be enough. If you want to increase the go up again. Fine.
Didn't seem happy at that end when it rose a little bit, so it wasn't fine. Okay, as you can see, clearly we've got a variation going across there in each of those. As predicted, the variation should be roughly the same size. Well, just roughly I can see that that's nearly 2 newtons across each of those gaps. That's a good sign early on. The top one, as I say, drifts upwards, so we might have to do further work on that. However, as we've already seen, these computers are very powerful tools. So now, if that's okay, we'll do a bit more detailed processing on each section to actually see just how good the results are for this.